Hi, good morning. I'm Dibyangshu, and this is a work with my supervisor Shivaram Kalyanakrishnan from IIT Bombay. So, as a motivation, look at this picture, which is that of polynomial roots. So, specifically, if you take the roots of all polynomials with degree less than equal to 6 and height, that is the largest absolute value of the coefficients, less than 5, then you get and plot all the roots on the complex plane, you get an image like this. So the brighter colors indicate more concentration of the roots, while the dimmer colors indicate uh, less number of roots. And if you look at these integers, for example 0, 1, you see those black patches. Those show that there are less accumulation of roots around those points. Now, if I zoom at 1, you see that on the real line also there is a gap. So we have been able to show that the gap has to be at least sub-exponential in the number of the degree of the polynomial and the height. Now what's interesting is this, that this bound directly translates to the upper bound of one of the classic planning algorithms, namely Howard's policy iteration. Okay. So I shall briefly give an introduction to MDPs, DMDPs and policies, and then we shall look at the method. So MDPs, Markov decision processes, are an abstraction of sequential decision making. They are used in everywhere in reinforcement learning, be it planning, healthcare and automated control systems. So formally, MDP consists of a set of states, set of actions, a transition probability function and a reward function. So we are interested in deterministic MDPs when the transitions are limited to 0 and 1. And a policy is a mapping from the set of states to the set of actions. We look at deterministic policies. So here is an example of a deterministic MDP. So a deterministic MDP induces a graph, a weighted directed graph. So here we have an MDP with 6 states and 2 actions. The actions are indicated by the edges brown and green. And a policy is a mapping from the set of states to the set of actions. So here it's a subgraph where every vertex has exactly one outgoing edge, which represent the actions. So the value of the policy can be computed using this linear set of equations, also known as the Bellman equations. And here we have the action value function, which also can be computed. So when the action value at a particular state is higher than the value of the state, we call it an improvable state. So if during iteration, if we switch any improvable state, it guarantees that we shall go to a better policy, that is to say a policy with a higher value. So simplex algorithms typically switch exactly one state at each iteration. But Howard's policy iteration is one which it takes a greedy approach and switches all the improvable states at every iteration. So formally, when Howard's algorithm goes from a policy pi to pi prime, the rule that it follows is it takes the max for every state, it takes the max q value, action which gives the max q value. So again, as an example from the earlier MDP, remember it had 2 actions. So we have a policy. Suppose we start at this policy, and the state 2 is an improvable state right now. So simplex takes that action. So it switches from the brown to this green action. And then next step, it switches the state 0 again. And lastly, it switches state 4 to reach the optimal policy. So it has taken, so there were it took 4 steps to reach the optimal policy. Now, if we take Howard, if we do Howard on this same, starting from this same policy, it finds that 0, 2, and 4 were improvable. It switches at once all three and it reaches the optimal policy. So we see Howard is more efficient in this sense, that it always takes a greedy approach, and that's generally the case. So this algorithm was originated in 1960s, and it's most intuitive. Like if there is an improvable state, you take that. And it's highly efficient in practice, but it has an exponential upper bound. And even for this simpler class of deterministic MDPs, where simplex has been shown to be strongly polynomial, but Howard still is exponential, while the lower bound is only linear. So what we show is that for deterministic MDPs, we show a sub-exponential bound parameterized by the bit size of the rewards. Okay, so recall the equation for Q values, which was given in this way. Now, if we take gamma, the discount factor, as a symbolic variable, then this function becomes a rational function. That is a ratio of polynomials, because it consists of a geometric sum, so it becomes a ratio of polynomials. Now consider the polynomial f of gamma, which is the difference of two Q values with two different actions. So this polynomial captures how preference between two actions would change with the discount factor. So if I vary the discount factor, how these preferences would change. Now this turns out that this polynomial is a polynomial with it's a ratio of polynomials with integer coefficients and bounded height. This is true for deterministic MDPs when the rewards are rational. Now, if we have a function and if there is no root in one interval, then the function cannot change sign. Now, if we consider the largest root between 0 and 1, remember the discount factor can vary only between 0 and 1, and if we take the largest root before 1, and then there is no more sign change possible between that interval gamma q to 1, because that's the last root. So therefore, if we have that last root, beyond that last root, there cannot be any change in action selection, because that's dependent on gamma. Now remember, Howard's action selection rule is taking the argmax at every Q value for every state. Now, because this polynomial is fixed, like the sign of the polynomial is fixed, it indicates the trajectory of Howard's also is invariant beyond this gamma Q threshold. Because if that doesn't change, this also cannot change with respect to gamma. Now, there exists a bound, strongly polynomial bound, for Howard's policy iteration in this format, where gamma is a parameter. Now notice here, if we increase gamma, like if we make it very close to 1, this can become very large, like this can become exponential. If we take a point gamma, say 0.99, very like a large number of 9s, this bound is going to go very high. Now what we have done is we have shown that the trajectory of Howard does not vary beyond a certain gamma, right? So this bound translates to, like this bound is equivalent to this bound for Howard's policy iteration. And what we do is we show a bound of on this gamma q to be sub-exponential in n, where n is the number of states and b is the bit size of reward. So that directly gives us a bound which is sub-exponential for Howard's policy iteration. So we have shown a sub-exponential bound for Howard's policy iteration for DMDPs, and this is significant because Howard's policy iteration has been difficult to show for decades. And but this technique cannot be generalized to stochastic MDPs directly, because the particular point that I had mentioned was that for deterministic MDPs we get a polynomial with bounded height, which we don't have for general stochastic MDPs. Also, for general MDPs we show a exponential lower bound, so which means that for the threshold, so which means that it cannot be directly translated. And this idea can be generalized to more higher number of players. So for example, 2 players zero sum stochastic games, they have already adapted this, and also this may help understand broader classes of RL algorithms. Thank you.
So thanks for the speaker. So we have plenty of time for questions. Okay.
Question of clarification, because I think that's something can you go back? If there is time, of course.
Yeah.
Problem definition. Yeah. So I did not understand where the policy comes into play here. How does it work?
So this, the first image, actually all the images, these are all policies. So because the states are indicated by 0, 1, 2 and so on.
So 0 and 1 are the rewards, or what?
No. Yeah, the rewards are on the edges. On the edges, and the vertices are the states. So the actions are the outgoing edges from the state.
So what is between the dashed blue and the straight brown? The different types of edges.
Yeah. So there are 2 actions for this MDP. One is indicated by brown and one is by green. So when I have drawn this, I have kept that color, the colors for clarity. They are the 2 different actions from an MDP.
It gets you to n plus 2 instead of n plus 1. Is that correct? The action 1 gets you to n plus 2 if you're in state n plus 2 modulo 2, modulo 5. Is that correct? No? Because we don't see action 1 in the first, we don't see in the first, the top left picture that the action 1 is available at state 2. I suppose it gets you to state 4.
Yeah. So there was a switch. So we switched from this action to this one. So because state 2 was improvable, simplex changed. It switched the action. That's the action switch happened here. Again, it happened on state 0 in the third step here.
There are these root separation bounds known in number theory, classical bounds for BMT and so on. How do you?
Yeah, so if general root separation bounds, they are between any 2 roots. But what we have done is, that's what helped us here.
Sure, but wouldn't that already also imply this?
Yeah, but that is more general because it's between all roots, so it's a weaker bound.
So that weakness is not sufficient for your proofs?
No. It'll give us a worse bound.
So what does it give? Like how much?
Exponential. Exponential. That's exponential.
So in that factor, what factor changes? Like in your?
So in will be e to the power n something. So instead of square root n.
No, I think the minutious bounds are also root n. So, again, I don't remember the stuff well enough, but.
So there is by Rump, there is a root separation, this thing, that is to the power n something.
Yeah, but there's also bounds by Mahler and Minuti. I'm not an expert, but.
Yeah. So it doesn't give sub-exponential. I checked that.
We have still, yes.
Thanks for the talk. I think on not the last slide, but the slide on the summary, I think you mentioned that you can generalize it to two-player zero-sum games.
Yes.
Can you elaborate a bit more on that?
So for two-player zero-sum games, they have so Howard's policy iteration can be used to solve two-player zero-sum games also. So generally, so this bound, the bound that I showed, this was by Ye. This bound was generalized to two-player games by Hansen, and so they had done that. So that analysis is almost like you can just mimic that analysis even here. And we can show directly, because we have a bound, better bound here, it will directly go to that one also. So what these guys have done is more they have done into Blackwell optimal policies and so on to get the bounds for two-player games, and it's a more general result which they have worked on. But for more general two-player games, like there are many variants, it may be possible to get similar bounds. That's what I meant.
Just to maybe some question or not question, would be correct to interpret the results of the relations over policy iteration as an allowing for minimizing internal regret? No? I mean,
That's in the learning domain, right?
yeah, well, you know, in real life you know what's the policy, right?
Yes.
No?
Maybe. I'm not.
I mean, sounds interesting.
Okay, so I think we can thank the speaker.
Thank you.